Bismillahirrahmanirrahim. Assalamu alaikum, students. Today we are going to discuss another important topic. So let me write the topic: Convergent and Divergent series. This is our today's topic. So let us discuss the idea. We have been talking about series which have a finite sum in the last two lectures. We have also seen that there are series which do not have finite sums. For example, we take this series 1 square plus 2 square plus 3 square plus 4 square plus so on. This series does not have a finite sum. Let me write it clearly. Does not have a finite sum. Now, if a series has a finite sum, if a series has a finite sum, it is called convergent. Convergent. Right? Otherwise, it is called divergent. Right? So when a series does not have a finite sum, it is called divergent. That means this series is divergent because it does not have a finite sum. Now it is important to know whether a series is convergent or divergent because some weird things can happen if we try to apply ordinary algebra to a divergent series. Suppose we try it with the following series: 1 plus 2 plus 3 plus, sorry, let me write it correctly. 1 plus 2 plus 4 plus 8 plus 16 plus so on. 1 plus 2 plus 4 plus 8 plus 16. This is a divergent series. Now, to understand which weird things can happen if we apply ordinary algebra to such a divergent series, we do certain things to it in order to understand the issue. So let this sum be S, then 2S is double. You have to double every term. Let me use another color here. It is 2 plus 4 plus 8 plus 16 plus so on. I have simply multiplied by 2 on both sides. If s is 1 plus 2 plus 4 plus 8 plus 16, then 2s is 2 plus 4 plus 8 plus 16 plus so on. Now 2s is also s minus 1, right? That means 2s is equal to s minus 1. If I now subtract s from both sides, I will get s equal to minus 1. It follows from this s is minus 1. Understand it? We are taking a divergent series. We want to uh, throw light on the weirdness of using ordinary algebra to a divergent series, and hence highlighting the importance of checking whether some series is divergent or convergent. So S is 1 plus 2 plus 4 plus 8 plus 16. 2S is 2 plus 4 plus 8 plus 16. It can be written as S minus 1. So that means 2S minus S, if you take this S to left hand side or you subtract S on both sides, that is one and the same thing. It will turn out S is minus 1. Now see the absurdity. S is equal to this infinite sum and S is minus 1. How can this be? This is nonsense, right? It is nonsense. So you can see what can happen when we apply ordinary algebra to a divergent series. So it is important to check the convergence of a series before applying any algebra to it, right? Now, let us repeat the definition of convergence. Let us repeat the definition of convergence more carefully. Let us call the terms of the series AN so that the series is A1 plus A2 plus A3 plus A4 plus so on plus AN plus so on, right? Remember that the three dots at after AN mean that there is never a last term. The series goes on without end because we are talking of infinite series. Now, consider sums Sn that we obtain by adding more and more terms of the series. Define S1 is A1, S2 is equal to A1 plus A2, S3 is A1 plus A2 plus A3, and so on. Sn means sum of n terms in the series, that is A1 plus A2 plus A3 plus so on plus An. Now each Sn is called a partial sum. Each Sn is called a partial sum. S1 is a partial sum, S2 is partial sum, S3 is partial sum, and you can see S1 means the sum of one term, that means just one term. S2 means the sum of first two terms, S3 sum of first three terms, and so on. Now you can see Sn is the sum of first n terms of the series. The letter n can be any integer for each n. Sn stops with the nth term. S1 stops with first term. S2 stops with second term. S3 stops with third term. Right? Since Sn is not an infinite series, there is no question of convergence for it. Try to understand it. This series is an infinite series. There is never a last term. So we talk of its convergence, whether it is convergent or not. But the partial sums themselves, Sn, is not an infinite series. So there is no question of convergence for it. Now, as n increases, this is important, as n increases, the partial sums may increase without any limit. Without any limit. As in the series let me name it 1 square plus 2 square plus 3 square plus 4 square. You can check yourself that in this case, as n increases, the partial sums increase without any limit. Let me show you. Let me name it as in the series 1. For series 1, you can see what is S1. S1 is just first term, which is 1 square, that's 1. So S1 is 1. What is S2? S2 is 1 square plus 2 square, that is 1 plus 4, that is 5. What is S3? It is 1 square plus 2 square plus 3 square. It is 1 plus 4 plus 9. 1 plus 4 plus 9. That is 5 plus 9. That is 14. And check it. It is 1 square. It is 1 square plus 2 square. It is 4 plus 1, 5. and it's 1 square plus 2 square plus 3 square, 9 plus 4 plus 1 is 14. Similarly, you can see S4 is 14 plus 4 square, that is 16. 16 plus 14 is 30. 16 plus 14 is 30. Right? When you add 4 square 16 to S3, I get S4. As you see, as you find S for larger and larger value of n, you see in this series, the partial sums go on increasing without any limit. Second possibility is the partial sums may oscillate as n increases. For example, this happens in this series. With series 1 minus 2 plus 3 minus 4 plus 5 minus so on. 1 minus 2 plus 3 minus 4 plus 5 minus so on. In this case, that is in this particular series, the partial sums are 1, minus 1, 2, minus 2, 3, and so on. 1, first S1 is 1, S2 is 1 minus 2, which is minus 1. Then you add in S3 plus 3 plus 3, minus 1 is 2. Then you go on calculating, the partial sums oscillate. You can see partial sums first go to 2, then they go to then minus 2, then 3, and you go on increasing n, you will see that the partial sums oscillate, right? Or they may have some complicated behavior, right? Now, one possibility is that the SNs may, after a while, not change very much anymore. The ANs may become very small, and the SNs come closer and closer to some value S We are particularly interested in this case, in which Sn's approach a limiting value. Say limit n tending to infinity, Sn is equal to S. Let me name it. I have used 1. Let me name it second. Limit n tending to infinity Sn is equal to S. It is understood that S is a finite number. Now, if this happens, we make the following definitions. What happens if Sn's come closer to some value as n tends to infinity? That value is S, which is a finite number. Now, if this happens in a series, in an infinite series, we make the following definitions. What definitions? First, if the partial sums Sn of an infinite series tend to a limit, S, the series is called convergent. Otherwise, it is called divergent. Second thing, the limiting value S is called the sum of the series. Sum of the series. Third thing, let me use another color here. The difference Rn is S minus Sn is called, Sn here, is called the remainder or the remainder of the n terms right? Now from second, that is this definition of the limit, we can see that limit n tending to infinity Rn is limit n tending to infinity, Rn is by itself S minus Sn. So when you solve it, first term is just S, second term is S. From second, limit n tending to infinity Sn is S. First term is S, second term is S, so it is 0. Let me Then circle it and name it as 3. So we define remainder this way, and limit n tending to infinity Rn is 0 when we make use of equation 2nd. So this is all for today. So I will summarize the lecture. We talked about in this lecture convergence and divergence. We first said that if the series has a finite sum, it is convergent, otherwise it is divergent. Then we talked about this particular series 1. We said it doesn't have a finite sum, it is divergent. Then we highlighted the issue of using algebra to divergent series. We see that leads to nonsense. Therefore, it is important to test whether the given series is convergent or divergent before applying any ordinary algebra rules to it, right? Then we defined the convergence more carefully in terms of partial sums. We said that if the partial sums tend to a limit, then the series is convergent, and if not, then it is divergent. We defined the remainder of the series is difference s minus Sn, and establish it that limit n tending to infinity Rn is 0. So this is all for today. I hope you are enjoying these lectures. Don't forget to like, share, and subscribe my channel. Can leave comment in the comment box. Thank you. God bless you. Assalamu alaikum.